Example 5. Studying motion along a line. In previous lessons, we have talked about how we can model particle motions given position with velocity and acceleration. Keep in mind that particle motion moves across a straight line, which means particles move forward and backwards, not up and down. So if our graph is moving up, then our particle is moving forward. If the position is below the x-axis, that means that the position of our particle is behind the starting point. So a particle is moving along the x-axis with the position function x of t equals 2t cubed minus 14t squared plus 22t minus 5, where t is always greater than 0 or equal to. So we want to determine the velocity and acceleration and then describe the motion of the particle. So first things first, let's go ahead and determine the velocity of our particle. So if you recall, velocity is the derivative of position. So v of t is then to be 6t squared minus 28t plus 22. Now, in preparation for what's going to come next in the describing of the particle, I'm going to go ahead and figure out where the velocity is going to equal 0 so we can determine where it's moving forward and when it's moving backwards. So we set this equal to 0, and you get 6t squared minus 28t plus 22. I'm going to go ahead and factor out a 2 and get 3t squared minus 14t plus 11. Then this is going to factor down to 2, 3t minus 11, and t minus 1. So from here I can solve and get t is equal to 11 thirds and t is equal to 1. So now to determine where our particle is moving forwards or backwards, we need to figure out where the derivative is increasing or decreasing. So to do that, we're going to make a sign chart. So we used 1 and 11 thirds. Now we need to pick some values. So I'm going to choose 0, 2, and 4. So go ahead right now, pause the video, and determine where the particles are going to be increasing and decreasing. All right, here let's check it. So f prime of 0 is going to be what? Do I actually care what the actual number is? No, I only care whether it's positive or negative. So I'm going to go ahead and plug it into my factored form. So I get 2 times a negative number times a negative number, and this gives me a positive number. So this is positive, so it's increasing. Now I'm going to check 2. F prime of 2 is 2 times 3 times 2 minus 11 times 2 minus 1. Well, I know this is going to be a positive. From right here, it's going to be a positive times a negative times a positive, which is going to give me a negative. So from 1 to 11 thirds, the derivative is negative. And now we're going to check f prime of 4, and we get 2. 3 times 4 minus 11, 4 minus 1. This gives me a positive times a positive times a positive, which is a positive. So then this is positive, so this goes up. Now what this tells me, in terms of particle motion, that right here we are increasing, which is the same as forward. Here we are decreasing, which is backwards. And here we are increasing, which again is forwards. This tells me that the particle stopped moving at 1 second and at 11/3 seconds. Okay. Now we're going to do the same thing for acceleration. So to determine acceleration, we're going to take the derivative of velocity. So a of t is then 12t minus 28. You set this equal to 0, and you can factor out a 4, and you get 3t minus 7. So you get t is equal to 7/3. Now we're going to do the same thing. We're going to make a sign chart. Where this is 7/3. So we have to pick a value on each side and plug it into the second derivative. So I'm going to choose 0, and I'm going to choose 3. So go ahead right now and figure out where the acceleration is positive and where the acceleration is negative. Okay, so let's try it out. So we get f double prime of 0 is going to be 4 times 3 times 0 minus 7, which gives us a negative. Now we try it with 3, and we get 4 times 3 times 3 minus 7, which is a positive. So we get that this is negative, this is positive, this is going down, and this is going up. This means that from negative infinity to 7/3, our graph curves down, and from 7/3 to infinity, our graph curves up. Or in terms of acceleration, we are slowing down. Oops. In terms of acceleration, we are decelerating, and here we are accelerating. Okay? So I want to go ahead and take a second to look at the graph of all these functions just to see if we're right. So let's look at the graph here. This is the graph of our original function. And right here we see that as we start at 0, which is right here, the derivative is positive because we're going up. Now notice that it's concave down because the slope of the derivative is becoming less. Right here, this is our critical point, and the derivative here becomes negative. So then where the velocity is still positive, but it's slowing down, then here the velocity becomes negative, and it's becoming more negative and more negative, which means we're actually going faster. We're accelerating, but we're going negative, so we're accelerating backwards. Then here we stop because the velocity is 0. But now we speed up. We're going faster and faster and faster until it just takes off. Okay, so now that we have all this information, we are going to do an analysis of our data. This is where the actual part of the problem comes in, because the question said, describe the motion. All we've done is make some fancy charts and kind of gotten some numbers, but now we need to describe. So, here we go. When x prime of t, the velocity, is greater than 0 on the intervals 0, 1 and 11/3, infinity. This means the particle is moving right. Then we have the interval x prime of t is less than 0 on the intervals 1, 11/3. This means the particle is moving left. When the second derivative is greater than 0, this means accelerating. When the second derivative is less than 0, this means decelerating. And if you ask any physics teacher, they'll always say there's no such thing as decelerating. There's only negative acceleration. But for our terms, we're going to say decelerating. And I don't want you to confuse these. This is very important. Do not confuse with speeding up. Accelerating does not mean speeding up necessarily. I'm going to talk right now what it means to be speeding up. When the derivative and the second derivative are the same sign, this means x of t is speeding up. When x prime of t and the second derivative are different signs, this means your x of t is slowing down. Okay, let me show you what I mean by that by using a graph. Again, here was our graph. Let's pull it up again. There's the graph. I put it right here. Here's our graph of the function. So let's talk about where we're speeding up and slowing down. First of all, let's notice that right here is one of our critical points. So I'm going to go ahead, I'm going to draw an asymptote here just to illustrate something. I'm going to put another one at our other critical point, which was 11/3, which about is right here. And then I'm going to do something else. I'm going to, in a different color, place another asymptote, which is about, let's be accurate. Where was our second derivative? 7/3. So our 7/3 is about, it's a little bit bigger than 2. We'll say it's about right here. I might be a little bit off. We're going to call that 7/3. Okay. Probably should have been closer to 2, but that's okay. So for the point I'm making, it's fine. Let's talk about what happens on this side of the graph. So on this side of the graph, we have that the first derivative is positive and the second derivative is negative. This means that the particle is slowing down. So right here, because you can see that we're starting at a speed and then we have to stop, so we have to slow down. Now let's talk about what happens in this section right here. Let's talk about what happens here between the critical point and the inflection point. Here we have that the derivative is negative and the second derivative is negative. This means that we are speeding up because it's becoming more negative faster. We're getting to the point now where we're come from a stop and we're pushing on the gas pedal. Imagine like a car, we're pushing on the gas pedal, we're speeding up. Now let's talk about what happens in here between the next inflection point and the next critical point. This is where it gets interesting. Notice that f prime of x is still negative, right? It's still decreasing, but the second derivative is now positive. We're concave up. This means we're slowing down again. We're slowing down because we have to come to a stop. Right here, we're going to be stopped. So you have to push on the brakes. You have to, or let off the gas at least. You have to slow down. Now let's talk about what happens in the rest of it right here. So here we have that f prime of x is positive and the second derivative is also positive. So now we are speeding up again. And this is kind of what I'm talking about when I'm explaining the particle motion. You need to tell me where the particle is moving right, where it's moving left, where it's speeding up, slowing down, accelerating, not accelerating, when it's stopped, when it's not stopped. All those things you need to tell me. But yeah, that's how you describe particle motion.